Good day. Today we're going to see and learn a bit about the need to kickstart performance monitoring. Performance monitoring. Now, when it comes to design permitting of a ventilation system, every emission which comes out from a plant which is identified to have airborne pollutants are to be notified to DOE. Now, this notification process is actually also an engineering design permitting process, whereby, first of all, upon the identification of the airborne hazard, the right type of geometrical shape of enclosure or right type of geometrical shape of an exterior hood to be decided to be chosen. Right after that, the proper capture velocity introduction, which would convey air outside towards the hood so that the airborne at the point of generation can be conveyed along, can be removed at the point of generation. Why are we removing at the point of generation? We're removing at the point of generation so that these airborne pollutants does not get introduced to the breathing zone of a worker. So that's why we design LEV. But based on that number, based on what we derived at the hood, is what is going to serve as a basis for everything else. The design flow rate is what going to serve as the major as the force or as the flow rate which will convert transport velocity in the ducting so that condensation doesn't take place, so that settlement doesn't take place. That same flow rate is what going to be used to size up your filter so that we have adequate amount of filtration velocity so that there is enough retention time so that the airborne contaminant can be captured at the filter surfaces or at the filter depth or the filter bed. Then right after that, we're going to have the efflux velocity, whereby we need to clear a plume rise and an elevated dispersion so that any residual airborne pollutants do not get dispersed towards the ground level concentration of a sensitive recipient so that we do not increase the pollutants in the environment. So now, once DOE gives us an approval, once we do the construction, now what we're going to do next is we're going to establish, the moment the system has been installed, we're going to establish a performance monitoring. The moment we kickstart, when we are doing the baseline, what we're going to do is we're going to work with the user to kickstart the performance monitoring. What is performance monitoring? Now, when we do the first test, assuming that once upon construction we have tested, and first and foremost, what we want to do is we want to check whether the actual operation meets the design numbers. Now, this is what a design number will look like, assuming that we have a fume hood and we design for these particular numbers for 80 to 100, for example. So we want to see whether we are meeting that 80 to 100. Transport velocity is above 1000, efflux velocity is above 8, for example. So we want to meet whether we meet the numbers. Once we meet the numbers, once we reach the peak, now this peak will serve as the upper limit. In fact, this peak is considered the condition we want to maintain the LEV system or the ventilation system throughout its operation. So this is the green line, the acceptable condition, or I mean the baseline condition which we want to maintain. The purpose of a baseline condition is for us to maintain, to work as a reference point, and for us to maintain throughout the entire operation. Now, so we take performance monitoring. Performance monitoring can be done in various forms. The most basic performance monitoring which is required by DOE for a general ventilation system, I mean, for a ventilation system which uses filters, absorption filters like carbon filters and what's not, they would highly recommend that these filters doesn't get clogged. Why? When it gets clogged, flow rate will drop. For example, a little bit of technicality, if you look at it here. Now, the system is designed for 550 Pascal. Assuming that it goes up to 600 Pascal. If you notice, if it goes up to 600 Pascal, what is going to happen is you're going to have the flow rate dropping. Now, when this goes up here to 600 Pascal, now the flow rate will come down here. So you're going to have a drop of flow rate of about 500 cmh. The 500 cmh will definitely affect your capture velocity, will definitely affect your transport velocity, will definitely affect your filtration velocity, and definitely will affect your efflux velocity. That is the reason why we need the baseline condition to always be maintained. So one is the very quickest, simplest way to do it is by taking the differential pressure at a filter. Assuming that we have a filter here, we take the differential pressure, the pressure at the highest point and at the lowest point. Now, what will happen here is when the filter get clogged, the pressure at the highest point will not change, but the pressure at the lowest point will change. For example, let's say at the baseline this is 9 and 8. Okay. Now when it get clogged, 9 will never change as long the fan is running. But let's say based on this clogging, it becomes 7. So now the differential pressure has gone 2. Assuming that it goes up to 6, now it has gone 3. So these numbers will keep going up. What is the upper limit? The upper limit is until it cannot deliver 80 feet per minute, or if it is designed for 80. If it is designed for 60 feet per minute, then it cannot meet the 60 feet per minute. What's the bare minimum? If you want to really look at the theoretical part, until the airborne has a is causing exposure to the worker. So that is the primary objective, you see, of our ventilation system. Now let's get back to the baseline. Yeah, so we can choose to take differential pressure. We can choose to take the differential pressure here at the filter, and we can keep recording it. On top of it, you also can do another performance monitoring by also taking the um, phase velocity, the capture velocity at the phase opening. Okay, phase velocity and capture velocity for an enclosure hood is the same. Yeah, it is the actual term is capture velocity, but since it's being taken at the phase opening, it is also called phase velocity. So now, when this phase velocity goes very much lower, that itself can also be used as a trigger point. So you can combine the anemometer reading taken at the hood and the differential pressure reading taken differential pressure, I mean, at the filter as the performance. All right. So now we have the upper limit and we have the lower limit. Again, what's the upper limit? Upper limit is the baseline condition. What is the lower limit? The lowest capture velocity point here, or the lowest efflux velocity point here. You see, these are the, so a point where it still can maintain basic bare minimum. For instance, let's say if I choose 80 here, 80 feet per minute, 1000 feet per minute, and 8 meters per second, or 1575 feet per minute. So these are the basic numbers which we need to meet. Now, when we install a filter, can we automatically say, oh, you must meet these numbers? You can only theoretically assume, but these numbers cannot be predetermined. These numbers can only be done via continuous monitoring. You see, engineering is an empirical design. It's an empirical, it is not absolute. So when it comes to actual, so we can use a rule of thumb, okay, 10% rule of thumb, or 0.5, 0.5, 0.5 as a rule of thumb, but we need to observe. You see, you observe. Now, as for DOE, you are supposed to do the differential pressure. As for DOSH, LEV assessment wise, monthly, once a month, you must take the bare minimum performance of your hood. You see, so if you are taking an anemometer reading, and if you are taking this, you must be able to correlate. When the DP goes up, anemometer reading goes down. So how low it goes down. So if it goes down up to 80, then it's about time for you to service. So you trigger that. You take charge of the control. So that's exactly how it works. So you can start out with a rule of thumb, but eventually you can control by measuring the lowest point of capture velocity. All right. So why this? So if you look at it, the gist of it is when the deterioration happen, okay, when the resistance is the system build up, okay, when the filters are getting clogged, the deterioration will take place, okay, but we don't want the deterioration to go below lower limit. So we set the lower limit. We don't want it to go below lower limit, because if it goes below lower limit, there is a possibility of airborne not being removed, but it will come out, and then it will get introduced the into the breathing zone of a worker. The DOE perspective, or from the environment perspective, now the basic flow rate, when resistance goes up, efflux velocity drop, the flow rates of the system, overall system will drop. When the flow rate of overall system drop, let's say our baseline efflux velocity is 10. So we don't want it to go below 8. If you go below 8, let's say it becomes 7.9, what will happen? There is a possibility of downwash to take place. Assuming that, let's say, the wind here is strong, and the wind is stronger than 7.9, if you can push it down, then I mean, what will happen is the wind will become superior and push the plume down instead. Okay, technically the plume is supposed to be going up and disperse at the elevated level, but when the wind become much superior than the flux velocity, then the momentum, the vertical momentum, it will push down. So you have a very low distance for dilution. So what will happen? Pollution will get the recipients exposed. All right. So that's all from us. How do you conduct it? Again, if you have a differential pressure, you take the differential pressure, but do incorporate your anemometer reading, or if you have a hood static pressure on top of the hood header, 1 to 2 inch, 1 to 2 times diameter from the hood. If you can install a pressure gauge, a static pressure gauge, that also would serve as a complementary data for you to conduct a very good, very effective preventive maintenance protocol. Good day. Bye bye.